Okay, you saw the title correctly. Yes, we are going to try to handle three sections in one day. 8.6, 8.7, and 8.8. 8.6 is about combinations, which is really a lot like something we've done before. 8.7 and 8.8 are so closely related. Actually, they're pretty closely related to 8.6. So this is all kind of like one topic, but just in sort of three different flavors. I'll try not to triple up the homework on you. Okay, so we got three ideas. First of all, here's the stuff I'm going to be asking you when you come to class. And really, see, I put the 8. This number 4 is really just one question that combines 8, 7, and 8, 8 into one thing. And check out what we're going to be doing. Take 3n plus 4 to the 5th power, one great big polynomial in one step. Pretty interesting stuff. Okay, so what is 8.6 about? 8.6 is about combinations. We did combinations. You saw probably combinations when you're looking at permutations on your calculator because it's the thing it's right next to permutations on there. NPR was for permutations. Permutations were for when you're doing things like trying to figure out how to arrange people in seats, or like you had all the letters of the word triangle and you're trying to figure out how many ways are there to rearrange those. And right now you're going, okay, what does this have to do with sequence and series? Why are we in this same chapter? I'll get to that. You'll see that by the end of the triple video here. How many ways can you rearrange those? Well, you've got how many things you can put in the first spot times how many things you can put in the second spot, etc., etc., etc. This is really, how many letters are there? 8. I got 8 choices for the first, 7 choices for the second, blah de blah de blah. So really, it's like 8 factorial, which is huge. If I wanted to have a 3-letter word from those 3 things, really, my handwriting is better than this. You know that. It's just sometimes this thing isn't as fast as I am. Okay, then I have 8 choices for the first letter. I have then 7 choices for the second letter, and I have 6 choices for the third letter. We call that 8p3, and that would be 8 times 7 times 6, which I don't care to do that either, just for now. You know what? I've got my calculator right here. So I might as well show you there that 8 factorial is 40,320. That's 8 times 7 times 6 all the way down. 8 NPR3, 8P3, that just means take the first 3 elements of 8 factorial. So 8 times 7 times 6, and it's this. And 8 permutation 3, 8 things to choose from, and we're going to pick 3 of them in a certain order. That means it's like I'm taking those 3 letters from the word triangle. Or if I have a group of 8 people and I want to pick 3 in a very specific order. You'll notice that 8C3 is also available on the calculator. It's right here. 8NCR3. Now this is going to be smaller. This is only 56. What this means to do is it's like how many ways are there to pick a group of 3 people out of a group of 8. But I don't care about what order they sit in. Just I want to take a sub-collection of 3 things from a group of 8 things. So back to here, it doesn't really make sense with the, I guess it does sort of with the word triangle. If we had, imagine these were Scrabble tiles. I just want to pick how many different groups. If I'm just going to reach my hand into the bag and there's 8 tiles in the bag, I want to pick out 3 of them. How many different ways are there to pick 8? And in this case, I care, like, picking TRI, picking that collection of things would be exactly the same as picking RIT. I would have the same group if I'm just caring about the collection. In these words, this something like TRI is really not the same thing as RIT. So when I count up permutations, I got to count these things separately, so that makes a huge list. When I go to then convert to the combination way, I think of things like the TRI and the RRT. I want to make those the same. So really what we actually do to calculate combinations is you take the permutation number, you take this 336, and you divide it by, I'll show you the formula in a second, but in this example, I'd be taking the 336, and I'd divide it by really, say for something like TRI, how many different ways this group of TRI would have shown up how many different times in the permutation list. It would have shown up like that. It would have shown up like, oh, whoops, that's all of them that start with T. It would have shown up like RIT. It would have shown up like RTI. This actually doesn't take that long. It would have shown up like ITR and IRT. And that's it. There would have been, for every collection of 3, and by collection I mean that's the really thing I care about when I'm talking about tiles here, each one of those collections shows up 6 times. So yeah, there's 336 ways to arrange these letters, but for every one of those arrangements, I end up getting 6 copies of the same collection. So I really only want to count that once instead of all 6. So I take 336 divided by 6, and I bet you $1 that's really going to be 56. What they do in notation, and we're talking about 8. I should write this way. 8C3 is 56, and really it's just a reduction of the permutation. It's like saying, I have this in the notes here. It's like we're taking this permutation number, which was n factorial, and then divide off the rest of them after we get to n minus r. They cancel each other out. We take the first r terms of n factorial. We take that whole thing, npr, and divide it by r factorial. And we divide it by how many ways were there to rearrange the subcollection. In this, there were 6 ways to rearrange the subcollection of 3. You could also notice this. 3 factorial happens to be 6. So really what I did here is I took 8p3, and the NCR really took that and just divided it by 3 factorial. That's another way to do that. Okay, this seems kind of complicated. Like, who on earth is ever going to care about combinations? But oh man, let me tell you, it comes back all the time. It's good for that. It's good for this thing in sort of counting and probability theory, which I could always count up. If I want to take a subgroup out of a bigger group, this is how many ways there are to do it, and I don't care what order they're in. Say there's 16 people in your FST class, I get to pick 6 of them to go on a, I don't know, have a special math party, and you don't really care if you're the first person picked or the 6th person picked. You get to go. So picking a collection of 6 out of a group of 16 is going to be 16C6. Okay. Yeah, I can explain this here about the different. This is kind of like the triangle thing, where if order matters, then I want to take a permutation. But if order doesn't matter, if ABCD is the same as ABDC, then I don't count them twice. That reduces my total count. How many totally different ones are there? There's only 52,000. But if I care about the order, where ABCD and ABDC are different, I have to count that separately. It adds a lot to the count, and I just take 35p4 and I get over 1 million. Okay, actually this is so common, this NCR, there's actually a special notation for it. It's just written that way. So if I was back here, I could also call this 8, and I think Khan Academy might do it this way, 8 choose 3. Our book likes to use the big C notation, but it's the same here. The calculator, I guess, is something like this, but this is a whole lot easier to write. You'll see it both ways. It's like sometimes you see S sub n, and sometimes you see the sigma notation. You got to be prepared for anything. Once you start looking at combinations and you start looking at, what's the pattern of this thing as we start to calculate all these, and remember these are all whole numbers, so it's not like the patterns start out crazy at all. They start out pretty small, like 0C0 and 0C1, and I mean that's kind of silly, but 1C1 and 2C1 and 2C2. You get answers that are very nice whole numbers. See where I'm getting at here? You get answers like this. This I could actually have constructed by doing that. 0C0. I wonder if I can get these two in the same frame. Maybe if I reduce the size a bit. So you can see both at the same time. One more. Okay, fine. 0C0. That's kind of like saying, okay, I got 0 things to choose from. I want to choose 0 of them. How many ways are there to do that? Well, there's 1. This element over here, I'll talk about why it's in a triangle here in a second. If I have 1 thing to choose from and 0 ways to choose it, there is actually 1 way to do that. And if I have 1 thing to choose from and 1 thing I need to choose, there's 1 way to do that. You choose it. Here, basically, you don't choose it. Here, you do. They both are considered to be 1 answer. So the choose 0 thing is always going to be, the answer is always going to be 1. For choose 0, I got 4 things to choose from. I'm going to choose 0 of them. Yeah, there's a way to do that. Don't choose anything. 1. Over here, I have 4 things to choose from and 4 that I'm supposed to be choosing. How many ways is there to do that? Well, 1, because you have to choose all of them. So this over here where the n and r are equal, that's going to be 1. That fraction turns out to be 1 when you do the combination fraction. This one's always going to turn out to be 1 because there's only 1 way to choose 0. If you did it with the factorial notation in the formula up here for NCR, it would always work out to be, where is it? It would always work out to be 1 also. You would see that. Remember, 0 factorial is 1. And this is one of the reasons they defined it that way. But then in here, if you start writing these lists this way, notice the list gets longer each time. On something where I've got a group of 4 things to choose from, my options of sizes of sublists I could actually be picking. I could choose 0, I could choose 1, I could choose 2, I could choose 3, or I could choose 4. So there's 5 different ways to sort of complete that. If I went to the 5th row, there would be 6 things to choose from. That's why they sort of start stacking at this pyramid that kind of goes infinitely downward. But if you actually try to figure out what these numbers are, like compute 3 choose 1 and 3 choose 2, and 4 choose 1 and 4 choose 2, you get this little piece of pattern up here, which is nice. 2 choose 1 is where it starts to get interesting, which is this one. You have two things to choose from. Choose one of them. How many ways are there to do that? Well, you can either pick A or you can pick B. There are two to pick. 3 choose 1. Of course, you got one thing to choose out of a total of 3 things in the bag, so to speak. You could choose A or B or C. Picking 2 out of a collection of 3 is actually the same, because it's kind of like deciding which one not to pick. There's 3 ways to leave one out, like there's 3 ways to pick one, so that's always going to be the same. For the same reason, 4 choose 1 and 4 choose 3 are the same, because this is having 4 things to choose from picking 1, or having 4 things to choose from picking 3 is the same number of choices, because this is like saying picking which one to leave out. So you see this nice symmetry here. And there's even some internal symmetry as you get down there. So each one of these rows is the same backwards to forwards. But the most striking thing about this triangle, and maybe the way the triangle is defined in some books, is if you wanted to sort of make this little pyramid, you notice if I'm going from any number to the one below it, or to find any number here, I can just take the 2 numbers above it and add them together. Notice how 6 plus 4 is 10, 10 plus 5 is 15, 15 plus 20 is 35. That's all kind of very nice. It just so happens that combinations behave like that. And it creates this little pattern of numbers, this little tree, so to speak, that's useful in lots of contexts. And we're getting to the sequence and series thing. In fact, you can see some sequence and series down these diagonals. This is just the sequence is always 1. This is 1, 2, 3, 4, 5, 6, 7, 8. This is 1, 3, 6, 10, 15, 21, 28, which maybe you've noticed before. It's a nice sequence. It's 1, and then this is 1 plus 2. This is 1 plus 2 plus 3. This is 1 plus 2 plus 3 plus 4. This is kind of like what you're getting on each day in the 12 days of Christmas. So that's come up before, and lots of other patterns like what you'll see. The one that we're going to talk about the most actually has to do with the binomial expansion. I'm already talking about 8-8. This is great. But before I get ahead of myself too much, let's talk about another way to define Pascal's triangle. You could say the r plus first term in row n is NCR, or n things chosen r at a time. So if I'm looking at the, I guess this would be this is first row, second row, third row. So I'm looking at the, I don't know, the 4th row. Here we go. The 4th row, the third, the r plus first thing. So this would be the 4th thing. If I want to find the 4th thing, I look at the r plus first. So r would have to be 3 here for the 4th thing. It's 4th row, 3rd thing. 4th row, r plus first. R is 4, would be 3. The 4th thing would be R. Yeah. So you can see how that goes. Actually, I would, instead of this little definition here, I would just study this. It always starts at 0. It always ends at n, and you have to cycle up through there. If I wanted to know the 5th thing in the 18th row, I know the top thing is 18, and I start at 0 and I count up, and it would be 18C4. So there's that. Okay, and then we're on to what is this good for? And it's good for this binomial expansion, which is the last question you're going to have to answer. I don't know if I'm going to get through this in 15 minutes. I think what I want to do is sort of hint at a little bit what the binomial expansion is, and I'll do a part 2 with more examples. Okay, so it turns out that you can expand crazy things like this thing you're about to do at the end of the video questions here. This 3n plus 4 to the 5th power, using Pascal's triangle, or using these combinations. If you remember, when you expanded way back in the day, you expanded stuff like, and they use x and y in this book. I kind of like the books better when they use a and b, but that's okay. X plus y to the 0th power, of course, is 1. X plus y, give myself some room. You see y here yet? X plus y, that's a y. To the 1st power is really just x plus y. So, yeah, it's x plus y. I'm about out of time here, but we'll do x plus y squared. X plus y squared, the whole thing, is really x squared plus y squared plus some junk in between. If you forgot the junk in between, shame on you. I will deal with you at the beginning of the next video.